Because today I'm going to be talking about the actual experimental realization of a variational quantum algorithm on one of Google's latest generations of quantum processors, which is called a Sycamore quantum processor. So the work I'm going to be talking about is covered in this archive paper that I've written here, which we posted in April. And it involved a large team effort. There were 77 authors on this paper, but I want to call out Nick Rubin in particular, who also played very much a leading role in this experiment. So let's see, do I have control of the, yes, okay. So I want to start giving a little bit of an overview of quantum computing rather quickly here, because I know that not everyone in the audience is really a quantum native per se. Whoa, these are, all right, these are not coming out in the order I expected, but yeah, so today quantum computers are in what we refer to as the NISQ era. So these are noisy intermediate scale quantum devices, which means that we can execute circuits on somewhat large systems, maybe up to 50 qubits, but there are errors that severely limit the size of circuits that we can implement. So last year, Google demonstrated a milestone that's referred to as implementing a quantum supreme calculation. This is a perhaps unfortunate term of art, which means that we're able to solve some problem, albeit a contrived problem, on our quantum computers that would be in practice intractable to implement with a reasonable number of resources on even a large classical supercomputer today. But ultimately, we're hoping to realize error-corrected quantum computation. So error-corrected quantum computers, as Sophia mentioned, are those where we don't really need to worry about errors, but there are some fairly large resource overheads for these devices. So today, we're sort of just at the threat. If you think of these different regimes in terms of the number of qubits required, today we're sort of just past the threshold of what's classically simulatable. So we can implement things on a bit more than 50 qubits. Anything less than 50 qubits would be classically tractable to simulate. But to have error correction, we're going to need to based on the error rates we have today, we'd need devices with on the order of hundreds of thousands of physical qubits. And we are fairly committed to building those devices, but they're probably a decade off at least. However, in the meantime, we're going to have devices that are in between what we have now and those devices with hundreds of thousands of physical qubits. So it's quite sensible to ask whether we're going to be able to do something useful with these devices. And we're not certain, but it definitely seems like it's worth a try. So that's what we're going to focus on here today. So in particular, I'm going to talk about a quantum chemistry experiment. I think this crowd is pretty familiar with the electronic structure problem, so I won't spend too much time on this. There's protons and electrons, they're interacting. We're going to be working in the Born-Oppenheimer approximation, so concept of an energy surface is well defined. And these energy surfaces, they allow us to understand chemical reactions and in particular predict chemical rates, which inform the mechanisms of chemical processes. But for this, we need fairly high accuracy, chemical accuracy, in order to reliably predict rates. But unfortunately, obtaining that accuracy is difficult often, especially for systems with strong correlation. So this is the regime where we might want to think about using quantum computers. So like with any computer, in order to represent the system, we're going to need to in order to represent it on a computer, we're going to have to confine the system to a basis. As many of you are surely familiar with, in chemistry, we often focus on using orbitals, like these molecular orbitals. And in my talk, we're also going to focus on using the second quantized Jordan-Wigner representation, which Sophia also mentioned. So here we're going to have one qubit for each spin orbital in the system. If the qubit's 0, it means there's not an electron there. If the qubit's 1, it means there is an electron there. So if I had 4 spin orbitals and 2 electrons, then the wave function would span, say, the 6 configurations that I've written here. But in general, this is going to grow combinatorially with system size. So everyone in quantum computing sort of loves doing these experiments where they especially take diatomics and they try to run some quantum chemistry algorithm and they compute the curve. I think I've shown something like 6 experiments here. There's some overlap with a similar slide from Sophia. But this is probably maybe maybe a fifth. There's probably at least 30 or 40 experiments now on quantum computers obtaining curves like that. And it's great to see the enthusiasm of people on all different architectures, on photonic systems, on ion traps, neutral atoms, superconducting qubits, spin qubits, trying to do this. But there is something I want to point out, which I think should give us a little bit of pause here, which is that prior to the experiment I'm going to talk about today, the largest quantum simulation of chemistry was performed in 2017 by IBM on 6 qubits. And until our experiment, which came out in 2020, still the largest was on 6 qubits. And that's despite, maybe 30 other papers in the meantime. So I think, this should sort of it sort of begs the question of, why are these simulations not growing as fast as you might expect? And I think the answer is because it's actually very, very hard to get these to work in the NISQ era. And I'll tell you a little bit about that. But first, I want to sort of ask the question of, why do we perform these small scale experiments at all? Because we have various ways of benchmarking how well our devices work. We know what the error rates of the gates and the measurements and things are. And these are small experiments, so it's not like we don't know the answer of the chemistry problem we're about to solve here. I think there's a number of reasons for this. For one thing, I think it's kind of important to force people that work on algorithms, like myself, but many in the community, to feel the pain of a real experiment and sort of develop intuition for the sort of things that might work, and of course to share that. Because there's really a lot of art in getting these experiments to work. They often don't work particularly well when you just implement them as the textbooks might suggest that you should. For instance, we write down circuits that have identity gates all over the place, just places where we're not implementing gates. But in practice, your experiments probably aren't going to work very well if you simply do nothing to the qubits at that point in time. You should probably be implementing, say, spin echo pulses to decorrelate noise and things like this. So I think, it's important to see how techniques like that actually play out in practice. But I also think an important aspect is that these experiments, they provide something of sort of a holistic device level benchmark to see how these computers are performing in the context of an actual algorithm. So, we of course benchmark the components of our device, like I say, the individual gates and measurements and these things, but different teams have different preferred metrics. Google likes to talk about cross-entropy benchmarking. IBM likes to talk about quantum volume. Ion trappers have other preferred metrics. And to some extent, these groups don't really like to use the other groups' metrics, and so it can be a little bit difficult to directly compare platforms. But something like quantum chemistry is something that more or less all of these architectures would like to do and are attempting experiments on. So it's sort of more difficult to hide the flaws in your architecture when you're really forced to demonstrate an experiment. So on one hand, it's nice to sort of compare where we are relative to competitors. So for instance, I think it's telling that despite a lot of experiments on ion traps, superconducting qubits have now implemented quantum chemistry experiments that are 4 times larger than the largest ion trapping experiments. But of course, we also want to sort of measure how far are the experiments we can realize today from experiments that might actually be classically intractable, which has to eventually be the goal. But perhaps the most compelling reason to do experiments on applications in the near term, I think, is to really study the effect that noise has on algorithms and to test ideas for mitigating those errors. In fact, this is going to be essential to get anything to work without error correction. And it's an aspect that you can't easily simulate theoretically, because generally speaking, we don't have particularly good models of what the noise on our device really looks like. All right, so what's the actual experiment that we focused on performing? Well, it's an example of a variational algorithm, which are the types of algorithms we just heard about from Sophia, of course, where you have a circuit that prepares a parameterized quantum state. You measure the energy of that quantum state, and then you use a classical optimizer to update those parameters in order to try to minimize the energy. But the particular variational algorithm we're going to focus on is a rather peculiar one that I'll spend a couple slides motivating here. In particular, the variational ansatz we realize corresponds to a basis rotation, which might seem like a strange choice at first. So if we started on a molecular orbital basis that looks like these molecular orbitals, for instance, then after we apply our circuit, it's as if we rotated into a new basis that could be written as an orthogonal linear combination of this original basis. So the unitary that realizes this can be written in a fairly simple form. It can be written as evolution under a non-interacting fermion Hamiltonian, where the coefficients of these terms here, these kappa values, are related to the coefficients of the linear combination of basis functions, according to the correspondence I've written here. So this isn't per se an obvious form at all, but it's one that you're probably familiar with if you've studied quantum chemistry or you've looked at the Thouless theorem, which essentially gives this result. So I should say further that if we go ahead and we use this variational ansatz and we optimize the parameters, the state that we're going to prepare is actually going to be the classical mean field state, or what chemists refer to often as the Hartree-Fock wave function. And the Hartree-Fock wave function is often the starting point for calculations in correlated electronic structure, but also the starting point for many quantum computations. And so often this is a procedure we run before the calculation even starts in order to find the optimal basis for the system. So you can always write down a variational algorithm in the way that I've written it down here. Usually we think about, in the case of Hartree-Fock, applying this unitary rotation to the Hamiltonian so that this phi can be a product state. But in this case, we're going to think about actually applying the unitary explicitly on the system. So the question you're probably asking right now is, why would we do this? Because Hartree-Fock is classically tractable, and the whole point of using a quantum computer, you might think, is to do things that aren't classically tractable. And of course, all of that is correct. But there's a couple of reasons why I think this is a fairly well-motivated experiment. So the first reason is, whether you're using a quantum computer or a classical computer, basis rotations of this form are a fairly ubiquitous primitive. They come up all over the algorithms that we implement in practice, and I'll tell you more about that on the next slide. But it's something we know we're going to want to do on larger quantum computers. We're going to be doing basis rotations in a decade, and so from that perspective, it's it's something that any insights we glean about how to do them better are going to be valuable. It's also, and I'll explain this more, a situation where we know how to compile the quantum circuits for this optimally. And I think that's nice because since there's sort of one preferred way of doing this, I think it will make a very good benchmark for the future. But another property is that since we're not starting in the Hartree-Fock basis, we're starting in some other basis and rotating into it. From the perspective of the qubits and the computational basis, the states we're preparing are still actually very entangled states. They just have some tractable structure that we happen to know about, but the quantum computer doesn't know about that. But that actually helps us out quite a lot, because it allows us to have some nice sort of analytical insights into the way the system behaves. And in some cases, we're able to understand what's going on with errors in a fairly complicated situation much better than we would be able to if it didn't have this sort of hidden structure. And finally, there are some regards in which this focus simplifies implementation of our experiment and allows us to focus on other aspects of realizing this experiment at scale that we probably wouldn't be able to get to at this point without, with focusing on a different ansatz. Okay, so a couple more motivation slides here. I want to explain a bit more why I'm so focused on basis rotations and think these are such an important primitive for quantum computers. So very often we use the orbitals from the Hartree-Fock solution, the molecular orbital basis, which is a very compact basis. So we don't need very many qubits to describe the system to high accuracy, but we get a complex Hamiltonian that has n to the 4 terms. Now, on a classical computer, that's usually a good trade-off, because you're often very concerned about the size of Hilbert space. You want a very compact representation. The number of terms in the Hamiltonian maybe isn't your chief concern. On a quantum computer, it's actually sort of the other way around. On the quantum computer, you're very worried about the complexity of the Hamiltonian, because that will directly scale the number of gates you need in your algorithms and the number of measurements you need to make to, say, measure the energy in a variational algorithm. So in the context of quantum computing, there have been some nice results showing much better performance by using other basis sets, for instance, ones that diagonalize the Coulomb operator. So for instance, these Gauss-lit basis sets from Steve White, or we have this PRX paper talking about a type of DVR basis and how you can use it for quantum computing. And of course, here you have a bit of a less compact basis, so you'll need to use more qubits, but in many ways it will simplify the implementation. But if you're going to use a basis like this, you probably still want to start in a good initial state, like the Hartree-Fock state, which means you're going to have to apply a basis rotation at the beginning of the circuit. It's the first thing you apply just to prepare the initial state for the rest of the simulation. And I won't really get into this, but often if you're going to simulate a Hamiltonian like this, for instance, for time evolution, the most effective way to do that in a quantum computer, the way that has the least Trotter error, involves applying a different basis rotation to diagonalize this kinetic operator. And you sort of, so you'll apply that basis rotation in the middle of the algorithm. And finally, and I'll say this is a little bit technical, but the whole point of this slide is just to say that basis rotations are important and you can forget about it after this slide. But if you don't wish to make this trade-off where you sacrifice compactness but get fewer terms, then you can look at this form of the Hamiltonian, which is sort of inspired by density fitting or the Cholesky decomposition of the Hamiltonian, where we can write the Coulomb operator as a sum of O of n different squared one-body operators, each in a different single particle basis. And that's the form of the Hamiltonian I've written here. And it turns out that the most efficient Trotter steps, say for performing time evolution of this Hamiltonian on a quantum computer, they are based on simulating the Hamiltonian in this representation, where at every step you need to make O of n different basis transformations. And finally, it turns out that the most effective strategies for measuring the energy in variational algorithms, they also use this form. They also need these basis rotations. So all of this is just to say this is a very important primitive, and it's going to come up even in correlated methods on a quantum computer. So how do we realize these basis rotations on a quantum computer? Well, we had a PRL a couple years back that gave a nice way of doing this. So often when you see a evolution under a Hamiltonian like this on a quantum computer, the natural thing you might think to do is to simulate the time evolution term by term, like using a Trotter type method. But that method is approximate, has some errors. It turns out that because these one-body operators form a closed Lie algebra, there's a more elegant way of implementing this evolution. And you can actually prove it's the optimal way of doing it. And especially when you're applying this operator to a state that is at half filling, which is what we're going to do in our experiment, you get circuits that will look like this. You have this pattern of gates that has this sort of characteristic diamond pattern, and it just gets bigger if you have more qubits, where each of these theta gates I've written here is a 2-qubit gate with a unitary that I've written here. And it's characterized by some angle theta. And you find that angle theta. I don't really have time to get into the details of it, but there's some step that you do before you put together this circuit where you compute these thetas as the angle which corresponds to Gibbons rotations, which you apply to these kappa matrices in order to diagonalize them. So you don't necessarily need to understand that. The point is that we have some way of, given these kappa values, deriving a circuit with a structure that looks like this. And in terms of implementation on our physical hardware, there we go. On our physical hardware, we have as native gate operations the square root of I-swap gate, which is a 2-qubit gate, as well as single qubit rotations around the z-axis. And you can realize this gate by using 2 square root I-swaps and 2 single qubit z interactions. And it just has gate depth 3. So that's relatively efficient. Okay, so finally, last thing before I really get into the results here is, focusing on this Hartree-Fock experiment, it allows us to simplify the experiment in some way. So normally to measure the energy in a variational algorithm, you'd have to measure the 1 RDM, which is the matrix whose elements are the expectation values I've written here, and the 2 RDM, which is the matrix whose expectation values are the 2-body correlators that I've written here. But when you know that your state is a single Slayer determinant, as we will, then you can always reconstruct the 2 RDM from the 1 RDM because there's no sort of cumulant component. So this is a nice simplification that will mean we need fewer circuit repetitions. The other thing, this is a fairly general principle, is that there are structure in these 1 RDM and 2 RDMs, which you can use to sort of identify and remove errors from the system. For instance, we know the trace of the 1 RDM has to be equal to the number of electrons in the system. We know that the 1 RDM and the 2 RDM have to be positive semi-definite. In the case of a single Slater determinant, we also know that the 1 RDM needs to be idempotent. And you can use these properties to sort of project the estimates of the RDMs you get to ones that have less noise. So for instance, in our experiment, we use a method called McWeeny purification, which is a way of enforcing the idempotency constraint on the 1-RDM. And while that method is not going to work for more general correlated systems, there are conditions in general on the 2-RDM which you can use to similar effect. And this is sort of underlying the whole field in electronic structure of N representability. So I think that's a really interesting topic. Okay, so now a couple words about our hardware, and then I'll get to the results, which will go by rather quick, actually. So we use superconducting qubits for this experiment. We use a chip that has 54 planar transmon qubits, which are tunably coupled in a square array. So this is a picture of our chip. We make the part with the wires using one process, that's the purple chip, and we make the part with the qubits using a different process, and then we flip the qubits over onto the wiring part and solder them together. So you can't really see the qubits because it's already bump bonded there. Here's a picture of the dilution refrigerator that cools down our chip to temperatures colder than interstellar space, which I always think is cool. And here's the CEO of Google standing there for scale. So we're particularly proud on our device of the error rates that we've achieved. So this is a picture of the 54 qubits on our chip. The X's are the qubits, and the rectangles are the couplers where the 2 qubit gates happen. And you can see that on average across the entire chip, even when gates are being executed simultaneously, all of the 2 qubit gates have an average error rate of less than 1%, which is definitely state of the art for the field. I should say we also collected most of the data through a cloud interface that our team has been sort of dog fooding at this point in time, using the open source projects from Google, Circ, which Circ is sort of what we use to compose our quantum circuits and implement them and simulate them, and OpenFermion. And OpenFermion is an open source project for, we call it an electronic structure package for quantum computers.
Brian, just letting you know, 5 minutes.
Okay, I'll probably go a little bit over that, but be well below the 35. So, all right, how well does the machine actually do? So I should say briefly what we focus on. We look at 2 sorts of benchmarks. One is hydrogen chains. So we make these curves everyone makes, but instead of just H2, this time we're able to go up to H6, H8, H10, and H12. And for the first time, we also look at simulating a chemical reaction mechanism. So we look at the isomerization of diazine and focus on distinguishing between 2 competing mechanisms for that isomerization, one with an out-of-plane rotation of the hydrogen, one with an in-plane rotation. So, okay. So I've already kind of described to you what these circuits look like. We go up to 12 qubits, so we doubled the size of the number of qubits compared to all prior work, and the number of gates in our experiment is more than 10 times prior work, so it is significantly bigger. So the first experiment we did was on these H6 chains. So here are the results for H6. This is the same size as the largest prior experiments. I will in the next slide describe for you, there's a couple different methods of error mitigation we look at here, and the different dots here corresponding to the different levels of error mitigation. And these are all efficient error mitigation procedures. And again, I'll explain what those are more on the next slide. We also look at H8, which has quite comparable performance, and both those popped up at once, but H10 and H12. So H12 is the biggest experiment that we did here. Okay, let's take a closer look at this data, and I'll explain to you now more what it means. So first, the yellow dots are correspond to no error mitigation, so that's just the raw data from the experiment. The green dots correspond to error mitigation by post-selecting on particle number. So this is a very simple idea. Because in our representation, the qubits that are 1 indicate an orbital is occupied. So if you measure all of the qubits, you just sample a bit string, you should always see that the number of 1s is equal to the number of electrons. And if you don't see that, you know there was an error. So the green dots correspond to, at the end, if you decide to just ignore all of the data where the number of 1s in your bit string don't add up to the number of electrons, you just throw them out. And that's a very simple form of error mitigation. We basically end up throwing out about 30% of the data, and you get the green dots, which are already substantially better. So the blue dots here correspond to the purification by the McWeeny procedure that I told you about, which helps correct some of the incoherent errors in the system. And finally, the red dots, which This picture looks like almost on top of the blue dots corresponds to further a reduction of systematic errors in the system by using the variational optimizer at the outer loop that Sophia was talking about. So maybe a closer look at these errors you can see here. So on the left, we're showing the error in the energy as a function of bond distance, and it's almost below chemical accuracy for most of these points. And then on the right, what we're showing, we're showing the infidelity, or 1 minus the overlap of the system we prepared with the system that we meant to prepare. And that's a metric quantum computing people really like to focus on. Usually you can't compute this efficiently, but because this is the Hartree-Fock state and it has some special structure, we can compute it efficiently. And it just shows you sort of how the different error mitigation techniques are improving things. Finally, we have a table where we're also showing how the we're showing what these fidelities are. The highest fidelity is 1. And one thing I want to call your attention to is we also compute an estimate of the fidelity just by multiplying together the per gate error rates in the circuit, which should give you an idea of how things are performing. And it's usually quite close to the performance we actually see in practice. And that suggests that, in fact, our component level benchmarking is working quite well. I'll skip through this kind of quick. This is just showing like the progress that the variational optimizer makes as a function of the number of iterations. And note that we have a special optimizer here that that is sort of leveraging gradient information from the 1RDM. And finally, here's the data we obtained for the diazine isomerization. And so, ultimately, we're able to, within the model chemistry, being Hartree-Fock, which is, of course, this very particular choice, we were able to correctly resolve the right mechanism. And, that's good. I think, that's exciting, I guess. We're still only on 10 qubits here, but it is the first time that anyone has attempted to do this in an experiment on a quantum computer. So I think that represents some progress towards what we'd like to do ultimately. Okay, so with that, that was all the data. So this is actually my last slide before opening up for questions. So let's sort of recap here on what we actually did and perhaps what we learned from this experiment. So the first point is simply that we realized the largest NISQ chemistry experiment by far. So if you're wondering what can quantum computers do in the near term today, they can do things that are maybe about this size, which isn't very large. I think they're good results up to about 12 qubits, but simple extensions of this method are probably unlikely to scale past about 20 qubits with the current error rates we have. Now note this is very different than error-corrected quantum computing. With an error-corrected quantum computer, we can prove all sorts of wonderful things that we can do. But we're only going to need a few 100,000 to 1 million physical qubits, which is something we're dedicated to building at Google, but it's going to take a while. So in this particular experiment, the ansatz that we implemented corresponded to a non-interacting fermion evolution, which when optimized prepares the Hartree-Fock state. So again, this is a totally classically tractable ansatz. The point is not to compete with a classical computer here. In fact, quite the opposite. Because it has this structure, we're able to understand a lot of nice things about how errors are affecting the system. In particular, we're able to design error mitigation procedures that significantly improve the algorithm performance in the presence of these errors, including a post-selection procedure, which we show in our paper really helps mitigate against T1 errors, which are qubit relaxation errors. This purification procedure, which really helps mitigate against T2 errors, which are coherence errors in the qubits, and variational feedback, which helps correct coherent or systematic errors. But again, still, I want to emphasize that based on this data, we might need something of a breakthrough to scale to the classically intractable regime for chemistry without error mitigation. Without error correction. But perhaps we just need even more insights about error mitigation. I think that's quite possible. And I do want to encourage you all to possibly think about ways that your expertise might help with this field, because well, there's a lot of quantum computing people thinking about this problem. In practice, some of the biggest successes we've seen have come not so much from the quantum computing side of thinking about these things, but coming from really deeply understanding the chemistry and sort of the structure of these problems. So for instance, insights about how you can use and representability conditions to try to remove errors from the system has helped us enormously. And likewise, I think there's a lot of opportunities for machine learning to potentially help with how we mitigate errors in these experiments. All right, so with that, I just want to thank my collaborators one more time, especially Nick Rubin, who I worked with him, but Nick, I think, is the person most responsible for designing and essentially leading this experiment. Also, Charles Neal, who's an experimentalist on our team who actually implemented the experiment, and Vadim Smeliansky, who's the device physicist or leads the device physics team that really helped with the calibration and control of the system for this work.